Alright, this leads us to some applications of exponential functions, and one of the more common ones that we'll see in a pre-calculus class, and at times even in calculus, is that on compound interest. Now, back in your Algebra 2 days, you have done some work with exponentials. You've probably seen the simple interest formula, which is interest equals principal times rate times time. This is the compound interest formula that I presented. You may have seen this before, probably have, in which the amount of money that you have in an account is equal to the principal times the quantity of 1 plus the rate of interest divided by the number of times it's compounded a year, raised to the power of the number of times it's compounded a year times the number of years. So you can see what each variable represents. This is the type of interest where you earn interest on interest. They determine the interest maybe every quarter, so in 3 months they figure out what the interest is. They add that on to the original amount, and now you have a new principal, and you're making interest on interest. And then it's compounded again, and interest on interest on interest, and so on down the way. Now, if you take this formula here, and you let the number of times it compounds, which would be here and here, if you let that increase and increase and increase, so it's compounded quarterly, then it's compounded monthly, then it's compounded weekly, and it's compounded daily, and it's compounded hourly, and every second, and you increase the number of times it's compounded each year, and you let that get big without bound, then what we have is called continuous compounding, and this formula turns into this formula, which I always kind of remember because it looks like PERT, where P is your principal, E is the irrational number, 2.71828 and so on, that we talked about in the previous video. R is still your rate of interest written as a decimal, and T is still your time in years. So I'm going to use these two formulas here to answer these questions based on this original setup. Suppose that $8,000 is invested and pays 4.5% interest per year under the following compounding options. And what we're going to do is we're going to figure out how much money there is. So this is your principal. This is your rate of interest. We're going to let P be 8,000. We're going to let R be 0.045. And in this problem, n is going to equal 1 because it's compounded once a year. In this problem, n is going to equal 4 because it's compounded quarterly. And in this one, we're going to use this formula because it's compounded continuously. So the amount of money in the account is equal to 8,000 times the quantity of 1 plus 0.045 divided by 1. Now remember, this is for T years, so we don't technically we don't have. I tell you what, why don't we say 5 years? I should probably add that in for 5 years. We'll figure it out then. So it's being in this account for 5 years. So what we're going to do is we're going to figure out how much is in there. So we're going to let T be 5. That would make the problem a little more interesting here. And so if T is equal to 5, then this is going to be n, which is 1 times 5. So this is going to be 1 times 5. And this, you're going to get your calculator out. This is going to be 8,000 times 1.045 to the 5th power, which is approximately, to the nearest penny, it's going to be $9,969.46. I did that in my head, as you might guess. Okay. Now, if we compounded quarterly, you would think that it should be more than this amount, because compounded quarterly means you're earning interest on interest more often. So I'm going to plug in everything the same, except this time n is 4, and I'm going to have A is equal to 8,000 times 1 plus 0.045, that's my R, divided by 4, this time to the 4 times 5 power. So this is going to be 8,000 times 1.01375, if I'm not mistaken, to the 20th power, which is approximately, and I'll do this one in my head, $10,006. To the nearest penny, if I'm not mistaken. Now, that makes sense. It's compounded more often. Well, this one's compounded a lot more often because it's compounded continuously. So we're going to use this formula. A equals, remember, the PERT formula. the principal is 8,000 times e to the 0.045 power times 5 for 5 years. And I'm going to get the calculator out again, and I'm going to figure this out. And it turns out not as much more as you might expect, but more. This will be approximately $18.58. Okay, you may remember from the previous video I wrote down a formula that you use to determine what E is. It's 1 plus 1 over n, all that quantity to the n power as n gets bigger and bigger and bigger. Well, think of it like this. If you put your money into a bank and you invest $1 at 100% interest, at the end of 1 year, you would have exactly, from $1, you would have exactly, well, not exactly, but to the nearest penny, $2.72, which is approximately E, because this will be a 1, and this will be a 1, and this will be a 1, so you're just going to get E. Alright, now up to this one, and I've done it, doggone it again. This is one off of the review. I keep forgetting to circle that example. An initial investment of $1,000 is appreciated for 10 years in an account that earns 15% interest, compounded this time semi-annually. Annually is every year, semi-annually is twice a year. Find the amount of money in the account at the end of the period. Well, I'm using this guy here because it's not compounded continuously. I get A is equal to 1,000 times the quantity 1 plus, now rate of interest is 15. That's a pretty high rate of interest. I mean, you're not going to find that at a bank unless you own the bank. And this is going to be divided by 2. And this is for 10 years. So that's a lengthy amount of time as well. So this is going to be 2 times 10. Now this is going to turn out to be 1,000 times 1 plus. This is going to be 0.075 to the 20th power. You can add those two together, but I'm going to get Mr. Calculator out about this time, and I'm going to get $4,247.85. Now that's an account that built some money up, because remember your initial investment was $1,000, and now you've got over $4,000 in that time span. All right. Those were both examples of exponential growth. In this next one, it has to do with radioactive and half-lives, and this is decay, or exponential decay. Cesium-137 is a radioactive metal with a short half-life of 30 years. That means whatever you start with, 30 years later, you have half of that amount remaining. So if you have 1,000 pounds in 30 years, you have 500 pounds. In a sample originally having 2 grams of cesium-137, the amount, which we're going to call A of T, which is in grams, of cesium-137 present after T years, so we haven't put in a specific amount here, is given by this formula right here. I'm going to write that guy down. A of T is equal to 2 times 1/2 to the T over 30. Alright, it says, how much cesium-137 will be present after 30 years, after 60 years, after 90? It's kind of convenient that those are multiples of 30, because 30 years is the half-life. So for part A, I'm going to plug 30 in for T, and I'm going to find A of 30. In part B, for 60 years, I'm going to find A of 60. And for part C, for 90 years, I'm going to find A of 90 right into this formula. I didn't even have to derive it like I did back here. So I'm going to plug 30 in. This is going to be 2 times 1/2 to the 30 divided by 30, which of course that's 1. So this is 2 times 1/2, or 1 gram of cesium-137 present, which makes sense because we started with 2 grams. Now in this example, in 60 years, I'm going to plug 60 in for T. So that's going to give me 2 times 1/2 to the 2nd power, 2 times 1/4, or 1/2 gram. And that makes sense again, because after the first 30 years go by, you have 1 single gram, so you should have half that amount 30 years later. And then 30 years later, I should have half of this. So let's see what happens if I plug in 90. Of course, that's 90 divided by 30 is 3. So this is 2 times 1/2 to the 3rd power. or 2 times 1/8, which is, oops, 1/4. This would be 1/4 gram. So we use this exponential application a lot for different kinds of growth and decay. These are not the only examples that you'll see of this, just for right now. And you'll get better at these, memorize these formulas, and practice, practice, practice.